So now we have another quick demo on the software timers. So what I have here in front of me is the API reference documentation. And so we can see that there's a lot of the similar sort of syntax that we've seen in the other APIs for like queues and whatnot, like the create, and there'll be a delete here as well, exactly. Now the software timers, they work in sort of two basic ways, right? You have either periodic or what we call one shot. One shot means it times, and then it runs the code once. Because the idea of a timer is at the end of its period, it has a function that it calls. So it's sort of like, it waits, and it runs a function. So a one shot means it waits a certain time, it runs its function, and then it doesn't run again. Periodic means it waits, it runs its function, and then it just resets again and waits again, and then runs its function just in a loop, right? And so one shot timers are very useful because we sort of set up the timer, we set the function, we do all the setup work, which is more code, and then we can just start reset it every time. So when we want to manually run the timer, we as a developer, we just reset the timer and get it going, and it'll count again and run its code. So we don't have to manually set up the timer every time. So it's useful in that way. Periodic are very much the same. We just set them up and we just set them going, and they just keep running, right? So really, the basis of it all really comes down to the timer create sort of function where we set up pretty much everything. So it's a very similar setup to what we would be used to seeing in like a task, in that it takes, for instance, a timer name, which is just some debugging human readable name that we give it. It's not really that necessary, so it can be whatever you want. Now the timer period, this is the amount of time that it ticks in ticks of the system. There is a useful macro which we haven't used yet, and this is to say, for instance, if your tick is a millisecond, you could just write in like, hey, I want a 1 second timer, so I'll put in 1,000 ticks. And we know that the period is a millisecond, and therefore 1,000 ticks is correct. But the thing is that if you change the frequency of your tick, of your sysTick, then then, for instance, the time that you've put into, or the period that you put into your timer will no longer be a second, because it will be shifted because you've changed the tick period, and therefore 1,000 ticks is no longer a second. So the usefulness of this milliseconds to ticks macro is that it will always generate the same period of time regardless of what your sysTick is configured to be. So we'll use this in a second, but essentially all this takes in here is the period of the timer. So this is the timer, the time that the timer counts essentially between being reset and the code and its callback function being executed. Now we're talking about this quickly, the one shot or the order or the sort of periodic timers, and the difference is this auto reload parameter that you pass to the create function. So if you set it to true, then it will the timer will sort of auto reload, meaning it will reset itself and it will run periodically with this timer period, right? If it's not set, and then it will go into it, then it'll be one shot, and as it says here, it will enter the dormant state after it expires, and so this requires it to be reset by the user. Timer ID. So this, I think, is when you pass in a the function call timer ID. Where is it? No, timer ID void const. What is this? An identifier that is assigned to the timer being created. Typically, this would be used in the timer callback function to identify which timer expired when the same callback. Okay. So this one sounds like it is the parameter that is passed the callback function, namely this here. Altogether with the API function save a value call between timers to the callback function. Okay, and then this is the callback function that you want to pass in. It needs the format void, which makes sense, and then it takes in the xtimer handle, which I'm assuming is used to reference things or to get values from within the function, such as calling these guys. Let's have a look at an example. I'm a bit curious about this timer parameter that we need to pass in. Where is callback, xtimer create, calling it timer, the period, bd true, the ID that is used to store a count of the number of times the timer has expired, which is initialized to 0. Okay, that makes sense. So here you can pass in a variable, or better said, pointer to a variable. As we will see here, it's a void pointer. So passing a pointer to a variable in there where the timer ID or the timer, this makes sense. But here they're using it differently. The ID is used to store a count of the number of times the timer has expired, which is, but that is counter to what is written here. This typically would be used as a timer callback to identify the timer which timer expired when the same callback function is assigned to more than one timer. That's what I assumed it would be, in that you can set the functionality of your callback to handle different timers, actual instances. So I think this comment here is false. And here you pass in some identifier that you create such that your code in your callback can, for instance, have a switch statement that switches between, okay, I have 5 timers, but I only want to use the same callback function for all of them. Then you can pass in this ID and switch between which timer you have, and therefore the functionality. I think for this example and for our purposes on this sort of basic level, we can just stick with what they have here, where we're passing in essentially 0, meaning that we just don't care and we won't use this anyway. But so let's go into a basic example, and we'll start by, like anything in free RSS, we'll need a handle to what we have, and so the type is a timer handle underscore t, timer handle, or no, timer handle underscore t. Does it exist? I will probably need to include timers.h. And then I should have, no, it hasn't found autocomplete yet, so my timer. Anyway, so now let's go ahead in my main function. Well, firstly, we'll create the callback function that we want. And it says here in the documentation, the callback function needs to have this format. So we need to have a void my timer callback, and it takes in a timer handle underscore t x timer. So that means it's taking in a handle to the timer itself that it's running. Therefore, we can use that handle within it to do things such as, maybe this function takes in the handle. Yes, such as we could call this function from within the timer if we so wanted to, right? So we can run, we'll put in some basic code, printf hello from the timer. And then what we need to do is we need to create the timer. So we'll do this in our main, similar to the task creation. I think we'll look at this example as a good reference. So we'll need the timer, the handle returned. So we'll say my timer equals x timer creates. Here it takes in the name, so we'll just put in my timer. This doesn't really matter. And so the tick we want, so let's say I want to run this every second, so we'll use pd ms to ticks. So what it seems, I'm going to put in the amount of milliseconds I want, and it will then convert this to the amount of ticks that I want. See, I'm currently running a kernel with a tick of 100 milliseconds, because for the other examples I wanted it to run slow so that it could be more human readable. So in this case, if I was to just put in what I think would be a second, like 1,000 ticks, and this would generate for me actually 100 seconds, right? And so I think, right? So this, in this case, will at least guarantee that whatever this time or the ticks that are put into this function resolve into an actual millisecond time. So I want 1,000 milliseconds because I want it to run on a 1 second basis. Now we'll start off by having its auto reload. So we'll have it set to PD true, meaning that it will wait, it will time, and then it will run the code, and then it will time and run the code, and we'll do this essentially without us intervening forever. Okay, so we'll typecast this parameter to a void pointer as required, but we should pass in a 0. like they've done, because we don't care about this. We won't use it. So my timer callback. And then we can run it. So here we go, we've created it. And we'll look in the example. The only thing that we do need to do is start it, because I imagine it will maybe say what state it is created in. The timers are created in a dormant state, exactly. So the timer start, timer reset, start from ISR, blah, 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 to transfer a timer into the active state. So I didn't know that change period started timer, but we do need to call the start or reset. Reset is generally what's used for when you have a one-shot timer. Starting obviously makes sense. So I didn't know that this actually changes it to the running state. Period active or dormant state timer, changing the period of the dormant state timer, and will also start the timer. That's a fun fact. Okay, cool. So let's start it. And so then we have the next line here. It will probably return, we'll look at the function, return a like a error code or error state. So returns PD fail will be returned if the start command could not be sent to the timer. Command queue even after block time has passed. Okay. So it must seem that this is the amount of time that we need to say, okay, try to create it and block if it doesn't. Should be held in the calling task should be held in the block state to wait for the start command to be successfully sent to the timer command queue. Should the queue already be full when it is called, the block time is ignored. So I am curious to know whether I can start this from my main, because I'm not in a task at the moment, because the scheduler hasn't been started. But let's have a try. So if X timer start, as you can probably tell, I haven't had much experience with timers. I haven't really ever needed them in my applications. I much prefer to use hardware timers because they don't have the overhead. So tick type, we want to block, we'll block forever. Port, actually no we won't. We won't block at all. And if equals PD fail, so if this fails, then we want to print timer start failed. So we know what's happened, and we'll just return an error code out of our program. Now let's have a look. We should be able to build this. Undefined timer create. Yes, because this I need to run my CMake again. Nope, still. Okay, I'm going to quickly fix this. Or X timer create have I called. So as always, the answer was directly in front of my face, written very clearly, but also somewhat hidden in the documentation. And so what I missed was this bottom line here, which says that to use timers, you need to set the configuration in your FreeRTOS config use timers. And so I was mentioning in the lecture quickly before that we have this config file called FreeRTOS config.h, and in here you can specify sort of the functionalities that you want to build into your kernel. And so for instance, I want to use mutexes, I use config use mutexes. What I've forgotten is to use config use timers. So I would assume that it was just in there, but it wasn't. And so I've included this, and now I'm getting a different build error, but this is actually quite good for us in an explanatory sort of way, in that now what it's saying is that config use timers is set, then we have, for instance, timer task priority, timer queue length, and timer task stack depth must also be defined. And so these are sort of values that are required, because from reading or from Googling this and clicking on the first hit, we can find this page where it explains how to configure my program to use them. And so there's this, for instance, the task priority. And so there is a task that manages the timers, which makes sense, and it also can be given a priority. So you can essentially set the relevance of timers in your system. Are they super important, or are they not very important? And so we, for instance, in our example, we can give it any sort of generic value, but then we also have to set the sort of the queue length, because timers are built on top of queues, and so we need to sort of just give it a length that we want to create for sending these commands. Because if you look into timers.h, I think, when I was looking into it a second ago, all of these function calls are actually just sending commands like command stop, command start, command delete, and these are just piped through queues. So a timer is just essentially, it uses a queue to send these commands, which makes sense because a queue is thread safe, and therefore by sending these commands through a queue, we can guarantee that we can send start and stop commands from all different tasks and we won't have any issues. So what I'm going to do now is I'm going to set these 3 required configure parameters. So we need task priority, queue length, and task step depth. So we'll just take you and put you into here. We'll say, okay, timers. Oops, hash define. I'll set him to like 1 because whatever. Define, and then we want queue length. I think for us it's also irrelevant. We'll just set it to 1. We won't be doing large amounts of high frequency spam for multiple tasks. And the last one, the stack depth. And so here we can probably just set this to, does it have a recommendation? Stack depth, set the size of the stack words, allocate timeout. So okay, the stack requirements of the timer callback functions. Makes sense. So that means that we need to set this large enough to handle a print statement. I don't think it's really going to need a stack because this constant string that we're printing is not going to get allocated to the stack of this function. It'll probably land in the constant or the read-only part of our program memory. So it's not actually going to land on the function stack. But what we'll do is we'll just be a little generous and say like 128 words. That's a lot of words for a function. And so this should now, if I haven't missed anything, build. Always read the documentation. Yes. So now if we run it, tick, 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 hello from the timer. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Perfect, because I have a tick of 100 milliseconds, and I set the timer to go off in 1,000 milliseconds, so in 1 second. So this actually works very well. Cool. So if we let this run, we should get every second, because it's auto reloading, this timer tick. Now, this is the very basic functionality of it, and so a more useful functionality is usually to do some sort of timing based off of some event. So you might have a periodic timer, but for instance, why I don't have much experience with FreeRTOS is that when I have a periodic timer, generally something that's just going to run uninterrupted, it makes much more sense to configure a timer peripheral on your embedded system, because then you completely take away the overhead from the software side of things, meaning your CPU doesn't actually have to count or check this timer. It's done like the systig, it's done by hardware with 0 overhead. But now let's create a timer and not make it reload. So what we'll do is we'll just change this PD false. False. And what we should see now is it will probably run once, and then that will be it. So it will no longer reload. And so what we can do is, for instance, we have demo task 1, and we can put in sort of a vtask delay here. Delay. And we'll delay him every 2 seconds. And we'll say print task is woke. And then what we'll do before he sleeps is that we'll actually reset the timer. So if we look at the reset function, we can see that it puts in the block time to call, and so as you can imagine, because now we know that these timers are based on top of the queue call, that this block time is probably the block time that is then passed to the send function for the queue, which makes a lot of sense. So what does it do? Handle and restarts a timer that's previously created using this. If the timer has already been started and is already in active state, the next time reset will cause the timer to reevaluate its expiry time, so is relative to the so it'll then essentially reset it will reset it to the beginning of its execution again, regardless of if it's running or not. So then we want to reset it. So x timer reset, perfect. My timer, and we'll say port max delay. Cool. And we could, for instance, we could do a check on this by thinking it won't fail, just to save us some time now. And so if we run this, we should see a lot of ticks, and then a message from our task, and then a second later, I'm missing something? Task is work, color from the timer, but where's my rerunning of it? Does it happen again? Task is work, color from the timer, 2 seconds has passed. Why is my demo task not waking up again? Is it still going? Oh, this is what happens when you don't use the macro, because I have a 100 millisecond tick, and 2000 ticks is a long time. So I'll do PDMS to ticks, and so I want 2000 milliseconds here. And so now this should work. So we'll have task is work, color from the timer, task is work, color from the timer, right? Which makes sense because there is a essentially 2-second gap between the task waking up and a second later it's running the timer because I woke it up, and so it runs for its 1000 milliseconds, and then it resets then every time that this the task wakes it. But now what we could do does the where was this changing? I want to say the change period. So it also, I remember reading before, it says that it also starts it. Changing the period will also start the timer. So what we can do is we'll do something a little bit fancy. We'll say I'll have like a counter int I. We'll set this equal to 1, and we'll have our we'll just do another integer like our base period. And we'll set this equal to PDMS to ticks, and we want to have our base period of 1000 milliseconds. Actually, I think integers probably we want to have even better. A timer period is the constant tick type. So now what we're going to do is we'll do something a bit fancy, and we'll go change its period and increment it every time so it gets quicker and quicker and quicker, because we know that, for instance, that this change period will also start the timer, so we can remove the timer start call and put in this instead: x timer change period. Timer we want is my timer. New period, so we'll take the base period and we'll we'll times this by I, and we'll plus I, meaning that after every time that I is read here, it will increment I, so every loop I will go up. And then the block time, we'll say port max delay, because this is the one that's used for the underlying queue stuff. And so now we should have a timer that incrementally gets quicker. So I go full screen on this. We should see that the timer slowly gets closer to the task is woke, but it's not starting the timer. To change the change of a dormant timer will also start the timer. Configure I am saying no, this is not happening, because unless our problem PDMS to ticks, the same problem again, most likely. Base period, but I'm also doing it here. So I'll just remove you. It's getting longer and longer. Times by I. I want to actually get it quicker and quicker. Here we go. Oops, up. So the timer is getting quicker and quicker and is slowly approaching this task's work. There we go. It should very soon sort of hit just directly after it as the period gets sort of logarithmically or inverse. There we go. And so now I guess we've hit the point where the period is actually so small that it triggers and then it blocks itself or goes to the dormant state because the tick that it's after is less than 1 tick, and therefore it goes active dormant straight away. So hopefully this, although it was a very hacky sort of example due to my lack of knowledge, it's quite easy. You can see that just from reading the documentation, you can usually figure your way through these things quite easily. So now that's pretty much everything wrapped up from FreeRTOS what we'll need, and I'll go through then sort of the example code or the example demo project that we'll be using.